Hi, and welcome to this EMTP webinar, Studies from A to Z. In this webinar, I will demonstrate how to use EMTP 3.4 in order to set up a differential protection relay. The protection library has been available since version 3.4. It contains many protection devices. We can see on the slide here the ANSI number for those protection. So we can find distance element, power swing and out of step protection, over voltage, under voltage, over voltage, or frequency, so under frequency, over frequency, rate of change of frequency relays, loss of field relays are models, as well as overcurrent relays, negative sequence overcurrent relays, or differential, which is the one we'll focus on today. EMTP type software offer very good environment to study protection. The first reason is that because the simulations are done in the time domain, they offer an accuracy which cannot be reached with phasor domain packages, which are the ones that are mainly used for protection studies. One aspect, for example, is that in time domain software, the influence of the switching time is important. For example, a breaker can open only at a zero crossing of the current. The closing time when we energize a transformer, for example, can be varied in order to simulate many different events and many different transients. So that's what we will do in today's webinar. EMT type software also provide very precise simulation in order to solve non-linearities. And that's a very big challenge when we talk differential protection and transformer energization. It's the non-linearity, which is from the saturation of the transformer, but also the saturation of the current transformer, which measure the current and provide the information to the relay. And we can also simulate the hysteresis. The goal of simulating hysteresis in our case will be to be able to determine the residual flux in the transformer, which can have an influence on the following energization. So in EMTP, in order to solve nonlinearities, we are using an iterative process. So at each time step, EMTP will iterate until convergence, and that will reach the maximum precision. And another very important point is that EMTP environment provides both the simulation of power devices and networks, but also control can be simulated in the same environment. And the protection library is a good example of that. All the relays are built using control diagram, which are actually accessible to the user for visualization or modification. And we will use those controls to create filters in order to filter the signal sent by the CTs and the voltage transformer, the VTs, but also calculate the different harmonic using DFT calculation or RMS calculation. So in the end, very precisely, we'll be able to reproduce with a very high fidelity what's going on a power system. So coming back to the differential protection settings, I group them into two classes. The first one I can call the basic settings. Those can be performed using traditional software packages. So they are the connection type in the differential relay. The transformer connection type has to be entered in order to compensate the angle between current at the primary and the secondary. So it can be a YD11 transformer, for example. You also have to enter in the relay the CT ratio at both sides of the transformer, the rated current as well, since most of the calculation inside the relays are performed in per unit. And also for numerical relay, you have the option to set up the zero sequence compensation. So we will discuss all that later on. And then there are the settings which are a little bit more advanced, which at least require EMT simulation. So those settings are the one to set up the percentage differential restraint. So it's the figure we can see here. So the pickup value, which is which correspond to this horizontal slope here, has to be set up. Then the two slopes, 1 and 2, also have to be set up, and usually typical data are used for that. The breakpoint in between also. And finally, the harmonic blocking function has to be set up. So what are those functions? Those functions are used to inhibit the tripping of the differential relay when for energization event or overexcitation event. When a transformer is energized, an inrush current will be created, which will actually create differential current. But there is no fault here, so the protection is not supposed to trip. But there is still differential current which is created, and sometimes the differential current reach the restraint current. So the harmonic blocking function will monitor the harmonic content of the current, and when this harmonic content reaches a certain threshold, which is the setting of the relay, the protection is blocked. So for energization, the signature of energization is in the second harmonic of the current. So that's the one which is usually monitored for harmonic blocking. However, fourth and fifth harmonic can also be monitored, and EMTP gives you the option to set up all of them. Okay, so here the benchmark we will work on. So we will not focus much on the network modeling. So we'll simply use an ideal voltage source and a short circuit impedance, but we'll focus more on the transformer itself and the protection. Then for a given study, each of you can model in more detail the network in order to get more precise results. So like always, we'll go ahead and build this network together. That will be fairly easy. So I have my EMTP open. I will go ahead and create a new default design. And I will start by saving it. You can call it circuit 1. Okay, so I will add the ideal voltage source and the impedance. So in the library sources, AC voltage source and impedance. Okay, the voltage level here is 138 kilovolts. And the impedance, I will select the negative sequence data. The zero sequence resistance is 5 ohm. And the zero sequence impedance is 20 ohm. So I have to switch the unit from Henry to ohm. Concerning the positive sequence, the resistance is 0.8 ohm and the impedance is 7 ohm. For the negative sequence, you can notice here I have a little display problem. What I can do here is simply zoom on the HTML in order to see it fully. So for that, I press Ctrl and hold the wheel of my mouse. And I can now see the full tab and enter the same negative sequence as the positive sequence. Okay, so that's pretty much it. My ideal voltage source and impedance is set up. So that will be an equivalent of the rest of the network. For more precise study, one more, I really recommend you to model that more precisely in order to get a more accurate frequency response. Then I will add the switch which will represent the breaker, energizing breaker. Okay, so I go in the library switches and simply use an ideal switch. This switch, we will close it at 0.1 second. And once closed, we will never open it. Okay, so now let's go ahead and add the current transformers and the breakers protected the transformer. Okay, reminding that that's the final network I'm building right now. So the current transformer can be found in the library. Can be found, on the library transformers, CT. Okay, let's rotate them. To rotate the device, you can simply right-click on it and use one of the options here, or like I did, use a shortcut. Then the breaker can be found in the library switches, control three-phase breaker. We use here a control breaker because the output of the relay will control the state of this breaker, open or closed. So now I can add my power transformer. So in the library transformer, I go ahead and select the three-phase nameplate input. Okay, by double-clicking, I can fill the data of the nameplate. So this transformer is a 50 MVA. The frequency is 60 Hz. The primary voltage is 138 kilovolt. The secondary voltage is 69 kilovolt. The total impedance is 9%. And we don't have any indication on the resistance here, so I will simply put a small value of resistance in order to reproduce the loss. Of course, it's better to put the real value. Here we have the option to model the magnetization branch, so in order to simulate saturation. However, in the first step, our goal is to set up the basic settings of the differential protection. So we will simulate an ideal circuit. Then when it will come to simulate the inrush current and the energization of transformer, we will enable those magnetization branch. I forgot to change the connection type of the transformer. Here it's a Y delta with an angle of -30, and the Y is grounded. Here, since we have a delta connection, we have a floating network at the secondary. However, what happens is when there is a delta connection and a floating network, the air around the transformer and the conductor actually act like a stray capacitance, which ground the network through the stray capacitance. So it's always a better idea to place this stray capacitance in EMTP in order to avoid mathematical floating condition. Even though EMTP can handle those conditions, it's better to avoid warning message. So let's add this stray capacitance right now. So in the library RLC, I can add a C non-polarized. Take a typical value of 1 nanofarad. This will have like a very little influence on the result at the end, and ground that. So that represents the stray capacitance of the air, and so I don't have a floating network anymore. Okay, and so finally, let's add a load. So for that, I go to the load models, drag and drop the PQ load RLC. This load is pretty convenient and simple to use. So the user enters the voltage, the power, and the reactive power, and automatically an RLC, well, a RL or a RC equivalent is calculated in order to respect those conditions. In that case, we will simply put a nominal load. So when we simulate this network, we are in the rated condition. So it's a 69 kV. I will put 45 megawatt of power and 20 megawatt of reactive power. So we see that the apparent power, it's almost 50 MVA, so that's the rated condition. Oh, I actually forgot to place the CTs and the breaker at the secondary. So let's do it now. I need to open this conductor. For that, I will use the little zap. So I go in the tab Home, Zap. The shortcut is Control and H. Open this circuit and add the CT and the breaker at the secondary. I can actually simply copy the one that are here and paste them on the other side. So I select them, press Ctrl C to copy and Ctrl V to paste. Before pasting, I can actually decide to change the orientation using the arrows of the keyboard. So let's do that. Go. I connect them together and connect here. Okay, that's good. Okay, so now our circuit is completely set up. So the first step here will be to determine what's the good ratio for the CT in order to protect this transformer. So going back in my slide, so now we have to set up the ratio determination. So remember, there are two criterions. The first one is that for the rated current at the primary, we want a rated current at the secondary of the CT of 5 amperes. But also the maximum current has to be less than 20 per unit. So let's first simulate the rated condition, see what's the primary current, the rated current at the primary of the CT, and so we'll be able to determine the correct ratio. Let's simulate this. So I go to the tab Simulate, Simulation Options, and here I select the time step. So for steady state simulation, like we'll do here, or transformer energization, we don't need to go to a very small time step. We can use 50 microseconds. We can actually use a larger time step if we need to run faster, but in that case, the network is so small, it's not really a challenge. And for the simulation time, same thing, no need to optimize. Let's simulate for 0.5 seconds. Okay, so now we're ready to run this simulation. The one thing we have to do first is to place some scopes. Okay, right before running the time domain simulation, scope has to be selected. So here we will look at the current entering in both CTs. So I go in the tab Scopes of the mask of the CT and check winding 1 current entering, and same thing here. So now we can go ahead and simulate that. Okay, so you see the simulation is very fast. So now let's look at the results. So for that, I will click here on View Scopes with Scope View. That will open Scope View. Okay, so 2 windows open, and we'll use the signals window in order to select what we want to look at. So we set the current in both CT. So we see in the signal type branch current, I look at CT1 and CT3. Here the network is completely balanced, so we simply have to look at phase A. So that's the instantaneous value of current when I energize. Remember, the saturation are not modeled here, so there is no inrush current or such things. So we go very quickly in the new steady state in order to determine the rated current. Actually, one thing which is more convenient to determine the rated current will be to display this current in RMS. So I will show you how to do that with Scope View. So go to the signal windows and simply click on the 3 dots there. That opens the Advanced Function Editor. In the category Mathematical, you can go ahead and select the function window RMS value. So this function calculates the RMS value over a period. So here we're at 60 Hertz, so the period is 1 divided by 60, and I simply have to select the signal I want to calculate the RMS on, add the function, and do the same for the CT3, add the function. And then I can plot that. We can superimpose those curves in order to see the difference. So I click once on the instantaneous value of CT1, then I press Ctrl, select the second one, and place them together. And I do exactly the same thing for the second one. So we see that in red we have the instantaneous value of the current, and in blue we have the RMS value of the current. So there is a ratio of square root of 2 in between. Now, using the pointer, let's have a look at those values. So the rated current going through CT1 is roughly 200 amperes, and the one going through CT3 is roughly 400 amperes. So going back to our simulation, according to those results, the ratios that respect the first criterion will be 205 for the CT1 and 405 for CT2, which actually is named CT3 in my case. So that's the first, to respect the first criterion. But now we have to make sure that at no time we will have a current higher than 20 amps. So 20 amps, which mean 100 amps at the secondary of the CT. So for that, we will simulate some worst case. The worst case are usually iron faults right after the CT. So let's place those faults and see the currents through the CTs. So I go back to EMTP, and in the library switches, I take an ideal switch in order to model a fault. Okay, I rotate the switch again using the shortcut of a rotating option. Connect it there. I add a ground. I can find a ground, for example, in the RLC library. And I close the CT in steady state and never open. We can actually close this breaker as well, because there is no need really to simulate the energization. Okay, so now I will find the worst current going through the CT, knowing that this breaker is an ideal breaker. So I go ahead and simulate that. And I go plot again those curves. So the worst current going through the CT is 13,000 approximately. Now I move the faults at the secondary of the CT3. So I open the conductor here, move the fault, place it here, and run again. And so now the current at the entering the CT is almost 4,000. So if I go back to the presentation, 11,000 amps entering the CT mean that we have, according to this ratio, 280 amps at the secondary. And so that's too much compared to the maximum, which is 100 that we want. So that's why for CT1, we will decide to change and to use a CT which is 605. Okay, and in that case, we would have less than 100 amps at the secondary. And so we know that we remain into the standard of precision of the CT. Concerning the CT2 or CT3, actually, in our case, there is no problem. So we can keep this ratio 405. Okay, so now I can get rid of this fault, and we can go to the next step. We can go to the next step of the work. So now the next step will be to actually add the differential protection relay and to set up the basic settings. So we go in the library protection, and we scroll down and take relay 87, 87 being the ANSI number for differential protection. So we drag and drop this differential protection and rotate it as I explained already, and connect the CT to the different inputs. So here the inputs, what are they? We have I1, I2, I3, which are phase current inputs. So we can use this device to protect 2-winding or 3-winding transformer. And then you have IG1, 2, and 3, which are ground inputs in case where you have a ground differential protection model as well, which is not the case here. You also have an input when you have a tap changer transformer, so then you can input the tap position in order to adjust the setting. And finally, we have here the tripping orders to connect to the breaker. So I connect the CT first, and then the breaker. Okay, so let's go ahead and double click on the relay. So that's here all the where we find the basic settings in the first tab, electrical characteristic. So the frequency in this case is 60 Hertz. The number of input, in that case, it's 2 because it's a 2-winding transformer. The connection type is a YD1 because it's a minus 30 degrees. We have no tap changer in that case. If we had one, we will have to put the number of tap position, the voltage per tap, and the voltage at minimum tap. Now we put the winding voltage, so the primary is 138. The power, the rated power of the transformer is 50 mega MVA. Okay, so the ratio we selected is 600 to 5, so we can simply write equal 600 divided by 5. Okay, the rated current, in that case, since we changed the initial ratio, which was, if I remember, 200, so now we divided the 5 by 1/3 in the end. So I divide that by 3. So do the same for the winding 2, which is 69, 50. Here this one was 400 divided by 5. Let me double check that. Yes. Okay, and the rated current is actually 5 in that case. Okay, so you also have the option here if you have a ground protection function. So in that case, you will have to input the ground CT ratio. Okay, if you want to really get in a lot of detail in your study, you can change here the input sampling of the relay and also simulate the quantizers. So simulating the quantizers in order to see the impact of the resolution of relays in the protection study. For modern relays, that's not an issue, so there is no need really of simulating that. Also, since there is a sampling function in relays, you also have to determine the anti-aliasing filter function. You can simply click on default transfer function in order to set it up automatically. Okay, so let's. I think we can go ahead for that now. So the second tab we'll set it after. So it's the differential setting. The ground differential current, we can still enable it, but we won't set it up now. We see that we enable the zero sequence compensation. I will go after to the tripping logic function, but let's go first to the scopes. So here we want to make sure we set up our basic settings properly, which means that when we run a simulation without fault, because everything is ideal in that case, we should have a zero differential current. So what I will do in that case, I will scope the differential current in order to see if I have zero differential current. I also have to adjust the ratio of the CTs, which I haven't so far. So let's put this one to 605. And I can load a typical value of resistance. Same thing here, 405. And load a typical value as well. We will see after for the excitation curve when we get to the transformer energization. Okay, so I think we are ready to go. So we can run this simulation and we will verify that the differential current of the relay is 0. Okay, so I open scope view again. I close the advanced function editor. Because I added new scope, I have to refresh scope view. Then I can go in the library control, and I see here the differential on phase A, B, and C. I will scope them on a new page of scope view. Okay, so you see here we have 10 minus 5, so it's pretty much the precision of the DFT algorithm, etc. So it's basically 0, which means our setting is done properly. Let's simulate a mistake. So for example, let's say I didn't put the good connection type, and instead of YD1, I put YD11. Now if I simulate that, we will see the difference in the differential current. Okay, so you see now we actually have a differential current. the protection and the tripping because of that. So let's put it back to what it was, YD1. Okay, very good. So now let's add the saturation of this transformer just to see the impact on the differential current. It should change it a little bit. Also, we can put the saturation of the CTs. So both of those CTs are C200, class C200. So I click on load typical excitation curve in order to enter the curve that respects the precision defined by the standard. You can also simply, if you have the excitation curve of the CT and it's actually better, enter here point by point this curve. And I do the same thing for this one. Okay, so let's simulate that. And have a look at the differential current with the saturation. So you see now it's not 0 anymore, but it's still very small. Here we have 0.2% of differential current, 0.2 amps, sorry, which is due to the very small the little saturation in both the power transformer and the CT. So here you start to have an idea of the level of precision we reach using software like EMTP. Okay, so let's go back to our differential protection setting. So now we go to the second part, which is the percentage restraint settings. So this part, of course, it's a little bit more challenging and really require EMT simulations in order to precisely find and verify the different settings. Most of the time, the pickup value, slopes, and breakpoints can be set with a typical value. However, for the harmonic blocking function, strategy, and restraints, etc., it's really recommended to perform advanced studies like we will show later on in this webinar. Okay, so to understand what's going on when a transformer is energized, let's look at this very basic example of a single phase transformer which is energized. So this example is already built, so I will simply go ahead and open that. Okay, so what do we have? An ideal voltage source here of the same voltage as the circuit we've been building together, so 138 kilovolts. Then we have a current transformer here, which is also the same. We energize the circuit after at some point here, and we have the single phase transformer in order to understand what's going on. Right now the transformer is unloaded, so we simply have a voltage scope at the secondary. So a typical model of transformer is composed of an ideal unit, the impedance at the primary and the secondary of the transformer, and the magnetization branch. When we energize the transformer, some current will actually go through the magnetization branch, and that's how that can be misled with a fault when this energization is done. So let's simulate here and look at what's going on. So I simulate 5 seconds. Okay, we are done. So I actually prepare a scope view template so we can see the graph right away. So in scope view, you can actually save a template. So when you go back to the study, you open the template and all the graphs are already organized. So the way to do that, you have the saving option here and the opening option there. And it's usually saved as a XML file. So that's the one for me here. So you see for this template, I changed the police of the font. I arrange in different pages so we can really see what's going on. So when I energize my transformer, Here I'm looking at the current at the primary and the current at the secondary. So if we have a look, the blue line here is the current at the secondary, so it's equal to 0, of course, because the transformer is unloaded, so the current going out of the transformer is 0. However, you see as soon as we energize the transformer, we see a current at the primary, and so that's why in the end we see some differential current. The current in this, the current at the primary is asymmetrical, mostly second harmonic current. And now if we have a look at the current going through the magnetization branch, and more especially through the nonlinear inductance of the magnetization branch, you will see that it matches completely the current through entering the the primary. And in the same scope, we scope in the same graph, we scope the differential current. So you see that the differential current is directly the same as the current going through this magnetization branch. Here, the way we calculated the magnetization current, because it's a very simple single-phase circuit, we simply took the difference between the primary current and the secondary current. Here in this device, which is a current meter, you can find this in the library meters, current I function of the time. You can actually specify a base, so the output here is directly in per unit. So I just do the difference of the current in per unit, okay, and we find like that the differential. And one interesting thing is here there is no fault. Once more, we are just energizing the transformer, and as you see, the instantaneous differential current can actually reach almost 3 per unit. And that's one single case, so it can get pretty high. Now, another thing that I do is I look at the frequency signature of this signal. So for that, I run an FFT. For the one of you that don't know EMTP very well, you can calculate an FFT of a signal. It's very easy. You can either simply write here in the tab FFT, open the bracket and go ahead and select the signal. And here it will calculate the FFT. Or if you don't know the syntax, you can click on the 3 dots here, go and select harmonic analysis in the advanced function editor, and finally select the discrete Fourier. You have other functions possible where you can display the module of one particular harmonic as a function of the time, the phase, etc. And so here what is interesting is we see the fundamental frequency, and which is this spike here, and the second harmonic. We see that clearly the second harmonic is the most present in this, apart from the fundamental, is the harmonic with the higher magnitude for the energization process. Even though we can see as a harmonic, it's usually based on the second harmonic that the blocking functions work. And more especially, we will focus on the ratio between the second harmonic and the fundamental. When the ratio between this second harmonic and the fundamental go above a threshold, then the function will be blocked. So that's here we are looking at the current through the transformer. However, there is not only the transformer that saturates. Here we also have the current transformer. As you see, the current here is asymmetrical. And because of the asymmetry of this current, the flux inside the CT will increase. And that's actually what we can see on phase 2. As you see here, this graph is the flux going through the current transformer, and it's increasing because of the asymmetry. And at some point, we reach here the first saturation point, and so now the CT saturates, and so the flux cannot increase much more. And in this graph, it's pretty interesting because we plot the current in per unit seen here in the same graph as the current in per unit seen by the CT. Okay, for that, in scope view, I divided the current seen by the CT, as you see here, by a certain base. And so you see, when the CT is not saturating, the currents are exactly the same. But as soon as the CT saturates, we can see a big difference. What it means is when you simulate a transformer energization study, it will be a big mistake not to consider the CT saturation and to simply take the current scope of the current going inside the transformer without considering CT saturation. So it's very important to simulate both the saturation of the power transformer and the CT. Actually, one option you have when you're at that point, if I look at the current at the CT, if you have the chance to be able to do a waveform playback in a relay, you can actually directly generate this graph as a comp trade and inject those waveforms in an actual relay to verify the settings. That's really the ultimate way to verify a setting. So to do that, it's very easy. You just simply select this graph and you click on here the small export function. You select the format. So in that case, it's comp trade, but you can also export at MATLAB or an ASCII, or you have a lot of other formats. You give a name. Okay, you can then find where you want to put it, and you can export it that way. What's going on here? I think the problem is because of the FFT. I should remove here the FFT I calculate. And I should remove, I will demonstrate that right after. Let's first talk about that. Here what it is, it's we compare the current, the harmonic signature in the differential current and in the CT current. So what it means is we look at the harmonic inside this current, so which is the actual differential current of the transformer, with the current measured by the CT, so taking into account the saturation, which is what the relay will see. Okay, so it's interesting what we can see if we focus a little bit on the first, the fundamental and the second harmonic. So you see the fundamental first, we do a big mistake on the fundamental. Okay, so in blue it's the current seen by the CT, and in red is the real current seen by the real differential current of the power transformer. And same thing, we do a pretty big error in the second harmonic. And the important thing here is that the ratio between the second harmonic and the fundamental might be different as well. So that's why, again, it's very important to verify that. Okay, so I did this graph, so now we'll be able to export in ComTrade. Again, sorry about that. So this time it worked. Here the problem was because all the graphs were not the same size, because on FFT, the x-axis is the frequency, whereas here it's the time. So that is why I had to remove the FFT, and now I can export in ComTrade. Okay, so so that's pretty much it for the basic example. So it helps us to understand what's going on. Another thing that we can actually demonstrate here is the influence of the switching time. Here we kind of set up a worst case scenario when we energize the transformer at a zero crossing of the voltage here. Therefore, that's when we get the worst flux and the worst saturation of both transformer and CT. We can change slightly the switching time here. For example, I can put it to 60 milliseconds and simulate the same case. So let's, for example, look at those three graphs. So I can, if I select them, the three of them, and I click here on the small camera, I can take a snapshot of it. Now run the new simulation after I change the switching time, and I can compare the results. Well, and you see, it's very, very different. Here the flux, the CT doesn't even saturate, so it's a completely different scenario. So that is why when we study transformer energization, we cannot just simulate one switching time. We'll have to run a lot of simulation where we change the switching time so we cover all possible energization. there is actually another parameter which is very important to consider. It's the residual flux. Okay, when you energize the transformer, it means that previously the transformer has been de-energized. And because of the hysteresis of the transformer, there will be a residual flux in the transformer when you will energize it. So you can actually play with these settings. I will show you how you do that with the transformer model. But first, let's have a look at how we can model hysteresis in EMTP. So here again, I will open one of my examples. Okay, so it's very easy. I have the same model as before, but this time I took off the nonlinear inductance of the magnetization branch and I replaced it by the hysteresis. Here I have a function that helped me to build the hysteresis model. It's very easy. You just have to enter the minor. You just have to input the minor characteristic of the hysteresis, okay, in this function. Then you can run this case, so it will generate a certain file name with an extension is, and you simply have to go ahead and load this file here, and it will automatically populate this device. So that's pretty easy to do. The only problem is most of the time transformer manufacturers do not really communicate on those hysteresis loops. So you really have to be lucky. If you are really lucky if you have them. So if you do, I really recommend you to model them, because then you go one step further in the precision of your model. So let's have a look at what is going on here. So I can simulate this case. Okay, and I will, let's have a look if I have a template for this example. No, I don't, but it's okay. I can create my own template. So let's load that into scope view. Okay, so let's start by drawing the flux versus the current. So in EMTP, it's very easy. You can do that using scope view. If you know the syntax, you simply click on flux. Then here you write VS, like versus, and then you go and select the current. Okay. Another option, like always, is you go to search the function. So you can select the category all, and the name of this function is versus. So then you click here, you select the two signals, okay, the flux and the voltage, and then you click on add function and it will do the same job. Okay, so as you see here, we really simulate like precisely the hysteresis. What we simulate in that case is the transformer is initially connected and we have a load, okay, of 45 MVA, and at 0.5 seconds we disconnect this transformer and we'll have a look at the flux and the current through the switch and inside this hysteresis. Okay, so very interesting. So at first, what we see at the beginning, if I select those three graphs by control and clicking, and I zoom at the beginning, so here we are connected. Then at 0.5 seconds, I disconnect. And so what we see is that so the current goes through to zero and the flux also goes down, but it doesn't go to zero. It actually goes at one of the intersection over there. And then it remains constant, and it will remain like that for a very long time. So basically here, next time you will reconnect the transformer, the initial flux will be this value here. So you don't really need to run the simulation. You can simply take this value as a residual flux. However, it's nice to run the simulation, because if you model the hysteresis of the power transformer and then you also model the hysteresis of the CT, you can try to simulate some different disconnection events and see the residual flux of both of them combined, and then study the energization very precisely. Okay, in our case, what we'll do, and we'll base our study on worst case scenarios, so we will play with residual flux. Okay, so now let's focus on the setting of the relay, so more especially the blocking setting. So I repeat, the way when we energize a transformer, a differential current appears calculated by the differential relay. This differential current is due to the fact that when you energize a transformer, some current is going through this magnetization branch, and so is visible through the CT at the primary, but not at the secondary. Of course, this energization event is not a fault, so the protection should be blocked for those events. And the way protection relays detect the energization, it's by measuring, calculating the ratio between the second harmonic and the fundamental. When this ratio goes above a certain setting, then the protection is blocked. It's also possible to use the fourth harmonic and the fundamental, or the fifth harmonic and the fundamental to perform those blocking. Each manufacturers have a different strategy, but most commonly it's based on the second harmonic. So this setting has to be sensitive enough to recognize a magnetization inrush. However, it has to be selected and be able to do the differentiation between a fault and an energization. Because when a fault occurs, the CT can saturate as well. And when they saturate, they can also generate second harmonic. So the first step will be to run statistical study, so run batch simulation, in order to find the lowest ratio of second harmonic blocking to block for all energization events. And then, as a second step, we will verify if when we simulate fault event, we don't have any tripping. So to find the worst case, so we will vary the residual flux, the switching time, and look at both individual blocking and common blocking. I will come back on those two notions later on. Okay, so let's go back to our circuit 1. And so now we will simulate the energization of switch 1. So I will remove the load number 1 and connect this switch at 0.2 seconds. So let's run a first base case just to make sure everything is going good. I look at the scopes with scope view. Okay, so let's look at the differential current. Okay, you see when we energize this breaker, this transformer, we have some differential current. Okay, so now let's go in the transformer setting and enable the harmonic inhibit. Here, by the way, what we see is the transformer, the blocking, wasn't enabled. So that's why we energize transformer and we trip. So it's a wrong tripping. So now we will enable the blocking and we will base that on the second harmonic. As I said before, for the percentage inputs, we'll keep the typical one. So the differential current, the slopes, we keep typical value. According to what manufacturer, sometimes the restraint is based on the maximum of the current or the sum of the currents. In our case, it's the same because we only have a current at the primary. Actually, the characteristic also of the restraint can change. It can be a continuous characteristic or it can be a discontinuous one. Let's go back in the scope tab and let's try to scope a little bit. Let's scope more signals to be able to see more things. So for example, we can also scope the restraint current calculating according to this characteristic. we can also look at the differential, the second harmonic in the differential current. Here we have the Boolean of the blocking, and we can also look at the fourth, the fifth harmonic, etc. Okay, so let's simulate this event again. I refresh scope view. So let's plot the restraint current calculated by the relay and the second harmonic in the differential. Okay, so here we have the differential current on phase A, fundamental frequency. So we compare with the restraint. Same thing with phase B. We compare with the restraint B and phase C. Okay, so we see in each phase the red curve, which is the differential current, goes above the restraint current in blue. And now we can see the level of second harmonic in the current, in the differential current. So what I really need in order to do my to set my settings is the ratio between the second harmonic and the fundamental. So you can already use scope view and do some and divide the signal in scope view. However, because I do those studies often, I actually developed a small device that can do that. Okay, so for that I will open one of my libraries. So I go in option, library option, open library. Okay, let's go wherever I placed this signal, this library. So I put it there in the section webinar, and it's in transformer energization. I think it's in the benchmark here, ratio calculation. Okay, so now I have my new library ratio calculation with a device named ratio calculation as well, and I will place it inside the relay. So as you know, the relay is an open architecture. Okay, that's here the differential function with all the output there, and I can drag and drop this component there. Right now the relay is in read-only mode, so I have to remove the read-only mode. To do that, I simply try to move something, and this message pop up. I click on unlock, and I place my new component. Okay, so here I have to connect the differential, the harmonic in the differential current. So it's this bundle. I can copy and paste it. Then here the differential currents, which are calculated there. So same thing. I select them, copy and paste them. And finally the tripping requests, which are also there when the differential current goes above the second harmonic. Okay, so quickly here, what we calculate is as soon as a tripping request is sent, which means there will be a false tripping, we calculate the ratio between each phase and the fundamental, each phase second harmonic, and the fundamental. And when there is no tripping request, we just send a high number, which is 100 in that case, so we don't mislead it with one of the minimum ratio. Okay, so let's now simulate that with this new device. It's named ratio 1. I will put it on page 2. Okay, so you see if I place the three phases together, that's actually the minimum of the three of them. Not really need to look at it. So the energization occurs at 0.2. Okay, and so you see before energization we have no tripping request, so we have 100, even 200 here. And when we start having the energization, then we go to the real ratio. Okay, so we go low. We go very low at the beginning, so let's zoom at that point. Okay, so here that's the ratio. In red, it's the ratio between the second harmonic current in the second harmonic in the differential current of phase A with the fundamental. Okay, B is the one for phase B, and C is the one for phase C. So for the blocking function, you have two options. You can use individual blocking. In that case, each phase are blocked independently. For example, the phase A in red will have to be blocked for a threshold above 50%. Okay, then the one in green will be blocked for a threshold which has to be smaller than 35%, and the one in blue, which is B, has to be below 50%. So that's individual blocking. If I have a ratio here of 20%, for example, A and C will be blocked, but not B in blue, and so I will have a false tripping. Now the second blocking option is common tripping. The common tripping means as soon as one of the ratio is above the switching, so in that case we have the red and the green curve, the three phases are blocked. So individual ratio is more flexible for the blocking. However, when you use common blocking, you have to be careful of the fault condition, where when you have a single phase two ground fault, you can block one phase, and so it will block automatically the two other phases. So when you select this option, more studies have to be done later on. Okay, so according to the simulation, the threshold would have to be lower than 20% in order to block that. So now let's run the statistical study in order to find out for all cases what threshold have to be set so it blocks all cases. Okay, so to set up the statistical study, it's pretty easy. We go to option and we drag and drop the statistical option. Okay, in this device we select statistical. We find out the number of one we'd like to perform. So in our case, let's do 50. Usually I recommend to go more to 500 in order to be more precise. Okay, we want here to reproduce the real mechanical behavior of breaker. And when a breaker is closing, the dispersion of the closing time is a Gaussian distribution. So here we'll stick to sit for random number, so to Gaussian. Okay, and also the breaker can close at any time in a cycle. Maybe the voltage will be maximum, maybe the voltage will be zero, or maybe it will be in between. So here we want to simulate all these events. That's why we add an extra T offset on the closing time on a full period. Here it's important to do it on a full period. There is an option as well to do it on half a period because the current is symmetrical before energization. However, later on we will change the residual flux. And so the transformer will not be symmetrical anymore because of that. So then it's important to actually simulate, vary the switching time over the full period. Okay, so as a first step, we will simulate without any initial conditions, so without any residual flux. The residual flux of the power transformer, when you double click, you go in the tab IC, like initial condition, and that's where you can modify it. So right now it's at 0. Then later on, we will simulate when we put 0.8 per unit in one phase and minus 0.4 on the other. That's kind of a worst case scenario. Then you can also simulate in between scenarios. The more scenarios you run, the more confident you will be with your results. Okay, so the statistical option is set up. Now we will go in the breaker, and in the tab random data, we will define the Gaussian distribution of closing of this breaker. Okay, so we can actually keep the default value. So it's a dispersion of 1 millisecond on each phase. Okay, so now we can go ahead and run this case. So we will run 50 energization of this transformer, changing the switching time, and for each of them, for now, sorry, the residual flux is 0. So that's the part which will be a little bit long, but still very fast. As you see, it's running fast enough to be able to do a lot of simulation. To look at the result, we will use mplot. So here both CTs are connected, but obviously the current going through this one is 0. So it's really the current in this CT determines directly the differential current. Okay, so we are done here. So let's look at the results. Sorry, I've been talking a lot. So we double click on mplot, Windows pop-up. Here we have to select statistical simulation data and uncheck base case simulation waveform. So you click on OK and it will open mplot. Okay, so going back a little bit on the result that we found before. So here are a lot of simulation. Okay, for the individual blocking, we need to find the minimum for each simulation, the minimum of each ratio. Now, if we do the individual blocking, we'll need the highest minimum of the three of them. So in that case, it will be the red. So it's kind of the maximum of the minimum, but that's confusing. So in this case, for common blocking, it will be the red one, which is the highest minimum, and for individual blocking, each of them has their own minimums. Okay, so if we go to mplot, as I said, we need to go to the minimum, and because we are looking at control signals, it's in the section control underscore minimum. Okay, so if I do individual blocking, we have to look at each phase individually. So you select the three of them, place them in the Y selection, and you can plot the apps. Okay, so you can take more space and kind of zoom on the lowest case. So here that's when you kind of have to have good eyes. Okay, so I see it over there. So that's my minimum here. Okay, and so you can see the value, it's about 20%. So it's of course recommended to run more cases. A way to also look at them easily is to treat them individually. So if I look at only phase A, for example, it's easier to look it that way, each phase individually. Okay, and find like that the minimum. So according to this 50 simulation, the threshold when there is no residual flux on the transformer has to be below 23%, okay, for individual blocking. Now if I use a common blocking strategy, I can plot that as well. And as you see, it's way higher because here the three phases are considered. So in that case, it could be 58%. Now let's run the same simulation with residual flux. So the worst case scenario, which is realistic for residual flux, will be there's 0.8 per unit in one phase and minus 0.4 in the other. The summation of the three of them has to be 0. Okay, and so let's run this simulation now with the residual flux. So if you want to be very precise, you have to do that with different value of residual flux, and you can also play with the residual flux of the CT as well. So that's when having actual hysteresis model for the CT and the transformer is convenient, because you can first simulate the de-energization event, and so EMTP will calculate automatically the residual flux and then simulate the energization event following that. So that's another approach. Here we base our approach on worst case scenarios, so we play with different value of residual flux and look at the results. Okay, so let's go again in the individual one. So let's look at phase A. So we should do that with phase A, B, and C. Here I do it only for phase A. Okay, so we see that this time we have a lower one. It's only 16.5. That's not a lot. Okay, and if I now look at the common blocking, okay, we can see here it's 30%. So according that this is the worst case scenario, I have to set up my energization, my blocking function at less than 16%. So let's say 15%. Okay, it's very low, but that's what it is, because it exists a case where you can have a tripping and where the ratio of phase A just go down to 16%. Okay, so in that case, I place the value here to 15%. So now where do we decide if we use individual blocking or common blocking? So in EMTP, you do that in the tripping logic. Okay, here you have the tripping for each phase, or you have the tripping logic for the 3-phase. Here, what we've written, so we have all the signals available here. We wrote that the 3-phase trip, when you have a differential current tripping for the phase, or a differential current tripping for the ground, and you don't have any inhibit. So for the 3-phase, without considering any differentiation. So now, if you want to perform an individual trip, what you will have to do is put 0 here, and for each phase, you will have to write here you want to trip the phase A if you have 87_PA and ground, and not inhibit of second harmonic, and you can also place a phase here, as you see, in between. Okay, so actually here automatically we check if the expression is good. So in that case I didn't do any error. Let's say I didn't write it properly and I put A like that, I will receive a message. So we check this expression. Okay, and so you do the same here for B and C. Okay, so you can really play with the logic you want. Okay, so now, again, I recommend you to simulate more cases than that with different simulation energization scenarios. Run mode, like you can go up to 300, 500 simulation when you energize, and that way really find the worst case scenario. Okay, so that's pretty much it. So we found here our second harmonic blocking level. In this toolbox, you can also use some manufacturer algorithm. For example, a lot of manufacturers use harmonic restraints. That's the case of Schweitzer, for example. So here you can put the harmonic restraint, which is based on the second and the fifth harmonic. There is also some special algorithm to detect internal or external faults. So you can also use the MTP to set up that. But we will not have time in this webinar to go into so many detail. Okay, so going back to my PowerPoint, so we've done all of that, and so now we are at the stage of verification. Okay, so there are three very important things to verify. So the first thing is when you do now you have your second harmonic ratio, your second harmonic blocking ratio set up. You have to make sure that when you have an iron fault which will saturate the CT, you are not blocking the tripping because of that. Okay, so how do we do that? We simply put a fault at the secondary of the CT. So I go in switches, I drag and drop an ideal switch to simulate my fault. Actually, in version 3.5, there will be a device name fault, so it will be even easier than that. Okay, I close this fault in steady state, and I never open. Actually, let's close it at 0.2 seconds. Now my transformer is energized. Okay, and let's place back a load so we are in a certain loading condition. Okay, so I put the same data as before. Okay, so let's simulate that. Oh, I forgot to disable the statistical simulation. Actually, we can also have a look at the flux through the CT to see if we have a lot of saturation. Okay, I open scope view again. Okay, so interesting. So here we see that when we energize or when we have the fault, so we have a pretty high value, of course, of restraint in blue and a very high value of differential. So here we are in tripping condition for the three-phase. We see that we have a high level of second harmonic as well, okay, almost 2 per unit of second harmonic in each phase. But it sounds like we are actually opening the fault because as you see, we clear it. So this test is, it's good that way. So that's for individual blocking. Now we could also check if we do for common blocking. So for common blocking, the lowest level of second harmonic was 50%. And so you can here put the 50%, change back the tripping logic to common blocking and simulate the same event and make sure that the protection trips for all kind of faults. So same thing here, I recommend you to test with different residual flux. Actually here I forgot to set up back the residual flux, but it's okay, it didn't have a big influence. So do like the more simulation you do at that point, the safer you are. You can also do a statistical study, and I recommend that, on the occurrence of the fault. So you really like cover as many scenarios as possible. Okay, so a second event which is pretty important to simulate is the energization of the transformer while there is a single phase fault. When the transformer is energized, for example, for maintenance or any other intervention, maybe you can have one faulty phase without knowing. And when you energize the transformer, the two other phase without fault will have a pretty high value of second harmonic current and will block the tripping. And so you have to make sure that the tripping is not blocked, especially in the case where common blocking is used. Okay, so let's unbalance that fault now. Click on never. So we'll keep the fault on phase A and we'll remove the two other phases. Okay, so we will energize again this guy at point 2. Actually, the fault on phase A will be there already, so we have to put -1 to say that the fault was there in steady state. Okay, so let's switch back to the common blocking function. Okay, so I put 0 to all of them, and here I go back to the common blocking function, so I remove A everywhere. And so for common blocking function, usually you can use a higher level of second harmonic level. So in that case, I think we could have put like 25%. Let's set to 20%, which is more typical. Okay, so let's simulate one, and we have to make sure that we trip in that case because we have a fault. Okay, so it sounds good here. Sounds like we tripped our simulation. Then, of course, like always, the statistical study will have to be run here. So we are sure that for each energization possible, when there is a fault on one phase, the protection trips. Okay, so let's only do 20 of them because we are running out of time. But of course, here you will have to do 300 of them, change the residual flux condition, and do other simulation to recover everything. Okay, let's do only 20, as I said, and a look at if we tripped each time. Actually, what can I look at to see if we tripped? Here, let's place a scope and do that again. So I will take a control scope. Here it's a three-phase trip, so I simply have to look at one phase. Call this scope trip. Okay, quickly I run again those simulation. Okay, so the last step that we will do for this webinar will be determine the sensitivity of our differential protection. So we will have a fault and we vary the fault resistance to see to what fault resistance our protection can detect. And so until what value, until what maximum value. Okay, so let's finish here at 30. See if we are sure we tripped at every cases. So I go to mplot again. Actually I can use the mplot which is there. To refresh it, I just plot something empty. Here I have my trip. I have to make sure to use control max, okay, because trip will go to 1 when there's a trip, and plot it. And so you see it exists few cases here where we don't trip. No, sorry, wrong interpretation. It exists few cases where we don't trip. Okay, so which means that, and it's actually a lot of them. So which means that here for common blocking, that we will not open the fault, so, because when we energize phase B and C, they block the 3 phase. So the tripping is blocked for the 3 phase. So here the common blocking will not work well. So I will have to switch back to individual blocking. Okay, so that's pretty interesting. Okay, so as I say, last step, let's see what level of resistance I can cover in my case. So I will place back the transformer in steady state, remove all residual fluxes. Here actually I was doing the energization with the load. Well, that's it's not the best, but it's okay. It's just as an illustration. Okay, and instead of having an iron fault, so the fault will be 3-phase again. Okay, it will occur at 0.2 seconds, but this time I will place a resistance. Okay, so let's move this guy a bit down so I have more space. And I will add a resistance. Actually, let's do it for a single phase fault. Okay, so what's going on here? Okay, so here what we will do is we'll vary the fault resistance, so increase the fault resistance until we see that the protection do not trip anymore. So which means that that will be the sensitivity of my protection. So for that I use a tool which will be available in the next version. So let me switch to this next version. I will save that. Okay, open the version, the future version 3.5. Even though it says 3.4, it's a developer version, so it's actually, there's the content of 3.5. And I will go ahead and open this. Okay, so we will run batch simulation, increase the resistance until we find the highest value which create a trip. Okay, and then the next value cannot be detected anymore. So that's just an information for the what type of fault we can cover here. Okay, so for that I will use something named batch process and the device which will be new named single parameter variation. Okay, so I open this guy. Here I will vary the fault of resistance R1. So this is what is called a configuration device. I select R1 and I will vary the resistance R1. Okay, and so I have two options here. I can vary step by step, or I can do what is called a bisection. Okay, a bisection is it's a way more efficient way to detect a limit condition. So here the limit is between trip and not trip. So I will use this technique, the bisection. Okay, I will start. So the low limit will be 0. The high limit I have kind of to guess. So I will put a very high value to make sure we detect it. And the convergence criterion will be, okay, if we have time, we can put 1, but here let's put 10 so it goes a bit faster. Okay, so when I say, okay, I have here a test pin, so that's the test pin will be 1 when we trip and 0 when we don't trip, so we connect that to the tripping output. Okay, and now we can go ahead, so we open this guy and start the simulation. Oh, I have to disable, sorry, the statistical, of course. Also, reset mplot, so we use the base case. Well, mplot will open, but we don't need it. And run this simulation. Okay, so it will take 15 loops to do that. So now we just have to be patient and simulate those 15 simulations. So first, here we put the resistance of phase A to 0. Okay, it's a phase for a single phase to ground faults. Okay, now we go to the higher limit, 50,000. Okay, now we'll get to in between. So it tripped at 0, but it didn't trip at 50,000. So now we go to 25,000. Okay, and apparently it didn't trip at 25,000. So we go to the between 12,500. Okay, and so like that, we'll precisely identify where we are. So now we try 66,250. Didn't trip. Okay, so now we go to 3,000 approximately. And it didn't trip, so it will take overall 1 more minute to really identify what's the limit for the phase differential protection to detect the fault. So what's the limit in the fault resistance? So of course that's for one loading condition. The good thing with this device is that you can cross the variation. So you can vary, for example, the resistance, but you can also vary the loading condition or other parameters, and you can do that for all possible combination of it. Okay, so now the maximum resistance is 97. We have 5 more simulations to go. Okay, 48. Okay, now we testing for 24, so that's pretty low now. I expect that the protection will detect that. Yes, it did. So now we get to 36. Then when you find this resistance, one way to change the sensitivity of your protection will be to play on the slopes. So you have the slope 1 and the slope 2 of your differential protection. If the sensitivity is not good enough, then you can lower the slope slightly. And of course, in that case, you'll have to do some more verification for other cases of energization, etc. But that's a way to change the sensitivity. It's to play with the slopes. Okay, so now my simulation is done, and so you see, so we requested a precision of a 10 ohms. So the sensitivity of my differential protection for a phase to ground fault is between 24 and 30 ohm. So 30 ohm it cannot detect it, 24 it does. I can run this simulation again, lowering the convergence test, so we get more precise results. It's just a matter of time. Okay, so that's it for this webinar. Sorry, I passed the time a little bit, but there was a lot to say on that topic. I really hope I was clear enough in my explanation and that you could understand everything. If there is any question remaining or anything else, we will stay online for about 10 to 15 minutes according to the number of questions. So please don't hesitate to use the chat box, the question box, to send us your question. We will stay there to answer. This video will be put on the YouTube. So if you're watching this video on YouTube, you can also ask questions. Simply contact sales@emtp-software.com and they will put you in touch with the good person. If you are part of a university, we can arrange a special partnership so you can use the MTP for minimal cost. According to the region, it's very likely to be free. So please contact us if you would like your university to get licenses of EMTP. If you're a professional and you would like to use the EMTP, you can request a quotation at the same address, sales@emtp-software.com. You can also ask for a trial license if you have some doubt on the capacity of the software. Finally, I remind you that we have an engineering team that can perform all type of engineering services going through time domain simulation, but also short circuit study or a steady state solution. We use all type of tools to be able to answer your request. Of course, all type of protection studies, we can do that for you. Just contact us at sales@emtp-software.com. Thank you very much for attending today's webinar, and I wish you a very good day. Bye-bye.